When the James Webb Space Telescope peers into the cosmos, it doesn't just capture distant stars, it peers back 13.5 billion years, to a time when the universe was a mere 300 million years old. In those ancient images, galaxies are still, their light struggling against the void to reach us. We see spirals and irregular shapes forming from primordial gas, their stars flickering to life in a sky dominated by darkness. The light from these galaxies has been traveling for over 13 billion years, each photon a time capsule from a universe less than 1/50th its current age. These snapshots reveal galaxies colliding, merging, and birthing the first stars, events that shaped the cosmos we know today. What we see isn't just far away, it's a window into the universe's earliest days, when time itself was still young, and the fabric of space was being stitched together. When the James Webb Space Telescope peers into the cosmos, it doesn't just look far away, it looks back in time. The images it returns captured galaxies as they existed just a few hundred million years after the Big Bang, more than 13 billion years ago. This revelation has transformed our understanding of the universe's earliest days, revealing a cosmos teeming with activity long before we ever imagined. But how does a telescope built in the 21st century peer back to the dawn of time? And what exactly did it see that has scientists so excited? Let's unravel this cosmic journey step by step. The key lies in the nature of light itself. Light, though incredibly fast, still takes time to travel across the vast distances of space. When we look at the stars in our night sky, we're seeing them as they were when the light left them, sometimes thousands, millions, or even billions of years ago. The James Webb Telescope is designed to look even further, deeper into the universe than any instrument before it. By focusing on the faintest and most distant objects, it can peer back to an era when the universe was still young, less than 1 billion years old. These galaxies, captured in stunning detail, are not just distant, they are ancient, remnants of the universe's earliest epochs. To grasp the scale of this discovery, consider the age of the universe. Scientists estimate the universe to be about 13.8 billion years old, a number derived from observations of the cosmic microwave background and the expansion rate of the universe. The James Webb Telescope's images show galaxies forming when the universe was only a few hundred million years old, just a fraction of its current age. These galaxies are so far away that their light has been traveling for over 13 billion years to reach us. In other words, when we observe these galaxies today, we're seeing them as they appeared in the early universe, a time when the cosmos was still in its infancy. What exactly did the telescope see? The images reveal galaxies that are vastly different from the ones we see in the nearby universe. These ancient galaxies are smaller, more irregular in shape, and often appear as bright, clumpy collections of stars. They are also incredibly luminous, which suggests they are forming stars at an extraordinary rate. Some of these galaxies are so distant that their light has been stretched by the expansion of the universe, a phenomenon known as redshift. This redshift acts like a cosmic fingerprint, allowing scientists to calculate how far away these galaxies are and how long their light has been traveling. The more redshifted the light, the farther away the galaxy, and the older the image we're seeing. One of the most astonishing findings from the James Webb Telescope is the sheer number of these early galaxies. In some regions of the sky, astronomers have identified hundreds of galaxies that existed just a few hundred million years after the Big Bang. This challenges previous assumptions about how quickly galaxies formed in the early universe. Earlier models suggested that galaxy formation took longer, but the data from James Webb indicates that galaxies may have formed much more rapidly than previously thought. These findings are reshaping our understanding of the universe's evolution, suggesting that the cosmos was already bustling with activity in its earliest days. But how did the telescope capture these images? The James Webb Telescope is equipped with advanced instruments designed to detect light in the infrared spectrum. Unlike visible light, which is blocked by dust clouds in space, infrared light can penetrate these clouds, revealing hidden structures and distant objects. This capability is crucial for observing the early universe, where light from the first galaxies has been stretched into the infrared range due to the universe's expansion. By capturing this infrared light, the telescope can peer through the cosmic fog and glimpse the first galaxies that formed after the Big Bang. Another key factor in these discoveries is the telescope's unprecedented sensitivity. The James Webb Telescope is about 100 times more powerful than its predecessor, the Hubble Space Telescope, in terms of light-gathering ability. This means it can detect fainter objects and capture clearer images of distant galaxies. The telescope's large mirror, which is more than twice the diameter of Hubble's, allows it to collect more light and resolve finer details. This combination of sensitivity and resolution has enabled scientists to study these ancient galaxies in ways that were previously impossible. The implications of these findings are profound. The existence of so many galaxies so early in the universe's history suggests that the processes of star formation and galaxy assembly were more efficient than previously believed. It also raises questions about the role of dark matter in galaxy formation. Dark matter, an invisible substance that makes up most of the universe's mass, is thought to have played a critical role in the formation of galaxies by providing the gravitational scaffolding needed to pull gas and dark matter together. The James Webb Telescope's observations may help refine our understanding of how dark matter influenced the early universe's structure. Moreover, these discoveries are providing new insights into the reionization era, a period in the universe's history when the first stars and galaxies began to ionize the surrounding hydrogen gas. This process, which marked the transition from a dark, neutral universe to one filled with light, is a crucial phase in the universe's evolution. The James Webb Telescope's images of distant galaxies are helping scientists map this era, revealing how the first stars and galaxies lit up the cosmos and shaped the universe we see today. However, these findings are not without challenges. Observing such distant galaxies requires overcoming the faintness of their light and the effects of cosmic expansion. The light from these galaxies is not only stretched into the infrared but also dimmed by the vast distances it has traveled. To counteract this, the James Webb Telescope uses advanced technology to amplify and filter the light, allowing scientists to study these ancient objects in detail. The data collected is also being analyzed using sophisticated computer models to simulate the conditions of the early universe and test theoretical predictions. In summary, the James Webb Telescope's ability to peer back in time has unveiled a universe teeming with activity in its earliest moments. The galaxies it captures are not just distant, they are ancient, offering a window into the cosmos as it was just a few 100 million years after the Big Bang. These discoveries are challenging existing theories, refining our understanding of galaxy formation, and shedding light on the role of dark matter and the reionization era. As scientists continue to analyze the data, they are uncovering new mysteries and deepening our connection to the origins of the universe. The journey of discovery is just beginning, and the James Webb Telescope is leading the way through the cosmos, one light year at a time. When we peer into the cosmos with the James Webb Space Telescope, we're not just looking at distant stars, we're glimpsing the universe as it was billions of years ago. This is because light, which carries the information we see, takes time to travel across the vast emptiness of space. The farther away an object is, the longer its light has been journeying to reach our eyes. And when the James Webb Telescope peers into the farthest reaches of the universe, it captures light that has traveled over 13 billion years to reach us. This means we're seeing galaxies as they were just a few 100 million years after the Big Bang, a time when the universe was still young, hot, and filled with glowing gas. But how did scientists confirm this? How did they build a telescope capable of seeing so far back in time? The answer lies in a combination of cutting-edge technology, decades of preparation, and the unique properties of light itself. The James Webb Space Telescope is a marvel of engineering, designed to overcome the limitations of its predecessor, the Hubble Space Telescope. While Hubble has revolutionized our understanding of the universe, it has certain constraints. Its mirror is only 2.4 meters in diameter, and it primarily observes in the visible and ultraviolet light spectrum. But the universe is expanding, and as it does, the light from distant objects is stretched into longer wavelengths, a phenomenon known as redshift. This means that the light from the earliest galaxies, which formed just a few 100 million years after the Big Bang, has been stretched into the infrared spectrum. To study these ancient galaxies, scientists needed a telescope that could detect infrared light with unprecedented sensitivity. Enter the James Webb Space Telescope, with its 6.5-meter mirror more than twice the size of Hubble's and its advanced instruments tailored to observe the infrared spectrum. This larger mirror allows Webb to collect more light, making it possible to see faint, distant objects that Hubble could not. But the telescope itself is only part of the story. The instruments aboard Webb are equally crucial. The near-infrared camera, NIRCam, for example, is one of the primary instruments used to capture images of distant galaxies.
It is equipped with advanced sensors that can detect faint light in the infrared spectrum, enabling scientists to peer into the early universe.
Similarly, the mid-infrared instrument, MIRI, is designed to study the faint glow of distant galaxies and the formation of stars in their infancy. Another key instrument is the near-infrared spectrograph, NIR-SPEC, which allows scientists to analyze the chemical composition of distant galaxies by breaking down their light into a spectrum. These instruments work in concert to gather data that reveals not only the existence of ancient galaxies but also their properties, such as their age, composition, and rate of star formation.
The process of confirming that Webb could see back to the early universe required more than just advanced technology, it demanded a deep understanding of how light behaves over cosmic distances.
One of the most critical tools in this endeavor is the concept of redshift. As the universe expands, the space between galaxies stretches, causing the light from distant objects to shift toward longer wavelengths. This redshift acts like a cosmic fingerprint, allowing scientists to calculate how far away an object is. For example, a galaxy whose light has been stretched into the infrared spectrum would be extremely distant, meaning it existed billions of years ago. By measuring the redshift of the light captured by Webb, scientists can determine the distance to these galaxies and, consequently, the time when they existed. This method has been used for decades, but Webb's sensitivity to infrared light makes it possible to study galaxies that were previously invisible to other telescopes.
The journey to confirm these findings was not instantaneous.
The James Webb Space Telescope was launched in December 2021, but its mission did not begin immediately. After launch, the telescope had to travel to its operational orbit, known as the Sun-Earth Lagrange Point 2, L2, a location about 1.5 million kilometers from Earth. This position allows Webb to maintain a stable view of the cosmos without interference from Earth's light or heat. Once in orbit, the telescope spent several months undergoing commissioning, a process of testing and calibrating its instruments to ensure they functioned correctly. This phase was critical, as any error in the alignment of the mirror or the calibration of the instruments could have compromised the telescope's ability to capture accurate data. The commissioning process involved meticulous adjustments, including aligning the 18 hexagonal mirror segments to form a single, precise mirror.
This level of precision is essential for capturing the faint light from distant galaxies. Once the telescope was fully operational, scientists began collecting data.
The first images released in July 2022 showcased the telescope's ability to capture stunningly detailed images of distant galaxies, including some that existed just a few 100 million years after the Big Bang. But these images were just the beginning.
To confirm that these galaxies were indeed from the early universe, scientists needed to analyze the data in depth.
This involved using the telescope's spectroscopic instruments to study the light from these galaxies in greater detail. By analyzing the spectrum of the light, scientists could determine the chemical composition of the galaxies, their rate of star formation, and even the presence of dark matter. These observations provided crucial evidence that these galaxies were not just distant but also ancient, existing when the universe was less than 1 billion years old.
The significance of these findings cannot be overstated. For decades, scientists have theorized that the early universe was filled with small, faint galaxies that eventually merged to form the larger galaxies we see today. However, direct observations of these ancient galaxies had been elusive until Webb's launch. The telescope's ability to detect infrared light and its unprecedented sensitivity allowed scientists to peer into the early universe and confirm these theories. The images and data collected by Webb have already revealed galaxies that are smaller, more numerous, and more actively forming stars than previously thought. These discoveries are reshaping our understanding of how the universe evolved in its earliest moments. But the process of confirming these findings was not without challenges. Observing galaxies from over 13 billion light-years away requires not only advanced technology but also a deep understanding of the universe's behavior. For example, the light from these distant galaxies is extremely faint, and even the most sensitive instruments can struggle to capture it. To overcome this, scientists had to develop new techniques for data analysis, including sophisticated algorithms to filter out noise and enhance the signal from distant objects. Additionally, the vast distances involved mean that any small error in the telescope's alignment or calibration could result in significant inaccuracies in the data. The meticulous attention to detail during the commissioning phase was therefore essential to ensuring the accuracy of the observations.
The collaboration between scientists, engineers, and technologists was another key factor in the success of this mission. The James Webb Space Telescope is the result of decades of research and development, with contributions from institutions around the world. From the initial concept to the final deployment, every stage of the mission required careful planning and innovation. The telescope's design, for instance, had to account for the extreme conditions of space, including the cold temperatures of the L2 orbit, which required the use of advanced thermal insulation and cooling systems. These systems ensure that the telescope's instruments remain sensitive enough to detect the faint infrared light from distant galaxies. As the mission continues, scientists are already planning for the next phase of discoveries. The data collected by Webb is vast, and it will take years to fully analyze and interpret. However, the initial findings have already provided invaluable insights into the early universe. By studying these ancient galaxies, scientists hope to uncover the processes that led to the formation of the first stars and galaxies, as well as the role of dark matter and dark energy in shaping the universe's evolution. These questions have long fascinated astronomers, and the James Webb Space Telescope is providing answers that were once thought to be beyond our reach. In the end, the journey of the James Webb Space Telescope is a testament to human curiosity and ingenuity. It is a reminder that the universe is full of mysteries waiting to be uncovered, and that with the right tools and determination, we can peer into the past and glimpse the origins of everything we see today. As we continue to explore the cosmos with instruments like Webb, we are not just looking at distant stars, we are uncovering the story of the universe itself, written in light that has traveled across the vast expanse of space to reach us. When the James Webb Telescope peers into space, it sees not just far away but far back in time. Its images catch galaxies as they were just a few 100 million years after the Big Bang, more than 13 billion years ago. This part of our deep dive into when the James Webb Telescope peers into space, it sees not just far away but far back in time. Its images catch galaxies as they were just a few 100 million years after the Big Bang, more than 13 billion years ago. Focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. When the James Webb Telescope peers into space, it sees not just far away but far back in time. Its images catch galaxies as they were just a few 100 million years after the Big Bang, more than 13 billion years ago. This part of our deep dive into when the James Webb Telescope peers into space, it sees not just far away but far back in time. Its images catch galaxies as they were just a few 100 million years after the Big Bang, more than 13 billion years ago. Focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. When the James Webb telescope peers into space, it sees not just far away but far back in time. Its images catch galaxies as they were just a few 100 million years after the Big Bang, more than 13 billion years ago. This part of our deep dive into when the James Webb telescope peers into space, it sees not just far away but far back in time. Its images catch galaxies as they were just a few 100 million years after the Big Bang, more than 13 billion years ago. Focuses on explore the open questions, scientific debate, and things that remain genuinely unresolved or mysterious. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. As the James Webb Space Telescope continues to unveil the cosmos, its revelations are only the beginning. The data it has already sent back, images of galaxies formed just 300 million years after the Big Bang, have already begun to reshape our understanding of the early universe. But these findings are not the final chapter. They are the first page of a much larger story, one that will be written by future missions, instruments, and observations. These upcoming efforts will not only build on what we've learned from JWST but also push the boundaries of our knowledge, potentially challenging existing theories and uncovering new mysteries. Let's explore what's coming next in the quest to understand the universe's origins and evolution. One of the most anticipated follow-up missions is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Named after the former NASA deputy administrator, this telescope is designed to survey vast swaths of the universe in infrared light, much like JWST. However, its primary focus is on dark energy and dark matter, two enigmatic forces that dominate the universe's structure and expansion. By mapping the distribution of galaxies across cosmic time, the Roman telescope will help scientists determine how dark energy has influenced the universe's acceleration over billions of years. This work is critical because the early galaxies JWST has observed may hold clues about the universe's initial expansion and the role of dark energy in shaping its evolution. If these missions reveal unexpected patterns, they could force scientists to reconsider long-held assumptions about the cosmos' fundamental forces. Another key player in this next phase of exploration is the Euclid Space Telescope, developed by the European Space Agency. Scheduled for launch in the early 2020s, Euclid will use its advanced cameras and spectrographs to study the large-scale structure of the universe. Its primary goal is to investigate the nature of dark energy by observing how galaxies cluster and how their light is distorted by the gravitational pull of dark matter. These observations will complement JWST's findings by providing a broader context for the early galaxies we've already glimpsed. For example, if JWST's images suggest that galaxies formed earlier than previously thought, Euclid's data could help determine whether this is a widespread phenomenon or an anomaly. By combining the strengths of these missions, scientists will be able to piece together a more complete picture of the universe's history, from the Big Bang to the present day.
On the ground, the next generation of large telescopes is also set to revolutionize our ability to study the early universe.
The Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of Chile, will be the largest optical and near-infrared telescope ever built. With a mirror over 39 meters in diameter, the ELT will have the power to observe objects billions of light-years away with unprecedented clarity.
This includes the faint, distant galaxies JWST has already detected.
By analyzing their light in greater detail, the ELT could reveal how these galaxies formed, how their stars evolved, and whether they contain the first galaxies ever to exist. Similarly, the Giant Magellan Telescope, GMT, set to begin operations in the 2020s, will use 7 massive mirrors to achieve similar feats. These ground-based observatories will work in tandem with space telescopes like JWST and Roman, providing higher-resolution images and more detailed spectra of the same celestial objects.
Together, they will allow scientists to probe the universe's earliest epochs with greater precision than ever before.
A critical tool in this exploration will be the technique of gravitational lensing, which has already played a role in JWST's discoveries. This phenomenon, predicted by Einstein's theory of general relativity, occurs when the gravity of a massive object bends the light from objects behind it, effectively acting as a natural magnifying glass. By studying how light from distant galaxies is distorted by intervening structures, scientists can infer the distribution of dark matter and the mass of these objects.
Future missions will refine this technique to study even more distant galaxies, potentially revealing galaxies that formed just a few 100 million years after the Big Bang.
These observations could challenge existing models of galaxy formation, which currently suggest that galaxies took hundreds of millions of years to form from primordial gas. If JWST's findings are confirmed by subsequent studies, they may indicate that galaxies formed much more rapidly than previously thought, requiring scientists to rethink the processes that led to the first stars in galaxies.
Another area of focus will be the search for the first stars in galaxies, known as population 3 stars.
These hypothetical objects, composed almost entirely of dark matter and hydrogen, are believed to have formed within the first few 100 million years after the Big Bang.
While JWST has already detected some of the earliest galaxies, the question remains, what were these galaxies made of, and how did they evolve?
Future instruments, such as the James Webb Zone follow-up studies and the upcoming Spica telescope, a Japanese-led infrared observatory, will attempt to answer these questions. By analyzing the light from these ancient galaxies, scientists hope to determine their chemical composition, their star formation rates, and whether they contain the first stars. These observations could provide crucial insights into the early universe's chemical evolution, which is essential for understanding how heavier elements were created and how they contributed to the formation of later galaxies and stars. The study of the early universe also raises profound questions about the nature of cosmic inflation, the rapid expansion of the universe in the first fraction of a second after the Big Bang.
While JWST's observations have already provided hints about the universe's early structure, future missions may offer more direct evidence of inflation. For example, the detection of primordial gravitational waves, ripples in spacetime predicted by inflationary theory, could be a game-changer. Instruments like the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory set to launch in the 2030s, will search for these waves. If detected, they would provide direct evidence of inflation and offer a glimpse into the universe's earliest moments. Such discoveries could bridge the gap between the Big Bang and the formation of the first galaxies, answering some of the most fundamental questions about the cosmos' origins. However, the journey to understand the early universe is not without challenges. One of the biggest hurdles is the sheer distance and faintness of the objects JWST and future telescopes are trying to observe. The light from these galaxies has traveled over 13 billion years to reach us, meaning it is extremely dim and requires advanced technology to detect. Even with the most powerful instruments, there is a limit to how much we can see. This is where the collaboration between different observatories becomes essential. By combining data from space-based and ground-based telescopes, scientists can overcome these limitations and gain a more comprehensive view of the universe. For instance, while JWST captures infrared light, radio telescopes like the Square Kilometre Array (SKA)
can detect faint radio signals from the earliest galaxies, providing complementary information about their properties and environments.
Moreover, the data from JWST and future missions will require innovative methods of analysis.
The vast amount of information collected will need sophisticated algorithms and machine learning techniques to identify patterns and extract meaningful insights.
For example, the study of high-redshift galaxies may involve analyzing their light across multiple wavelengths to determine their composition, age, and star formation history.
These analyses will not only help confirm existing theories but also reveal new phenomena that could challenge our understanding of the universe. If, for instance, JWST's observations suggest that galaxies formed earlier than expected, subsequent studies may uncover new mechanisms that accelerated their formation, such as the presence of dark matter halos or the influence of cosmic strings, hypothetical structures predicted by some theories of quantum gravity. The pursuit of knowledge about the early universe is also a collaborative effort, involving scientists from around the world. International collaborations like the James Webb Space Telescope's multinational team, the European Space Agency's Euclid mission, and the global efforts behind the ELT and GMT exemplify the spirit of scientific cooperation. These partnerships ensure that resources, expertise, and data are shared to maximize the impact of each mission. As new discoveries are made, they will generate new questions, creating a cycle of inquiry that drives the field forward. For example, if JWST's findings suggest that the first galaxies formed in a different way than previously thought, this could lead to new hypotheses about the role of dark matter or the nature of the early universe's density fluctuations. Ultimately, the study of the early universe is a testament to humanity's enduring curiosity and our ability to push the boundaries of knowledge. The James Webb Space Telescope has already opened a new window into the cosmos, revealing galaxies that existed just a few 100 million years after the Big Bang.
But this is only the beginning.
Future missions, instruments, and observations will build on these discoveries, challenging existing theories, uncovering new mysteries, and deepening our understanding of the universe's origins. As we continue to look further into space and time, we are not just exploring the cosmos, we are tracing the story of our own existence, written in the light of distant stars and the echoes of the Big Bang. When the James Webb Space Telescope peers into the cosmos, it doesn't just look far away, it looks back in time. By capturing light that has traveled over 13 billion years to reach us, it reveals galaxies as they existed just a few 100 million years after the Big Bang. These images aren't just distant, they're windows into the universe's infancy, showing how the first stars and galaxies formed in the earliest moments of cosmic history. What makes this possible is the sheer scale of the universe and the finite speed of light. Light from these ancient galaxies took billions of years to cross the vast emptiness of space, arriving at our telescopes today as they were over 13 billion years ago. This isn't just a snapshot of the past, it's a glimpse into the universe's earliest days, when the cosmos was still young, chaotic, and teeming with potential. The galaxies we see are not static, they're evolving, their structure shaped by the forces of gravity and the remnants of the Big Bang. By studying them, we're piecing together the story of how the universe grew from a hot, dense state into the vast, complex web of stars and galaxies we observe today. The James Webb Telescope's ability to detect infrared light is key here. Because light from these distant objects has been stretched by the universe's expansion, it shifts into the infrared spectrum, invisible to older telescopes. This technological leap allows us to peer beyond the limits of human vision, uncovering details about the first galaxies that would have been impossible to see otherwise. These observations are rewriting our understanding of cosmic evolution. Previously, we thought galaxies formed in a more gradual, orderly process. But JWST's images show structures that are surprisingly mature, suggesting that galaxy formation may have begun much earlier and more rapidly than we anticipated. This challenges existing models and opens new questions about the role of dark matter, the nature of star formation, and the conditions that gave rise to the first luminous objects. The data from these distant galaxies isn't just about their past, it's about their present. The light we see today is a message from the universe's youth, carrying information about its earliest stars, the first black holes, and the seeds of the cosmic web that now stretches across billions of light-years. Every image captured by JWST is a puzzle piece in a grander picture, helping us trace the timeline of the universe's development. But this is only the beginning. The data is still being analyzed, and each new discovery has the potential to reshape our understanding of the cosmos. As we continue to study these ancient galaxies, we're not just looking at the past, we're uncovering the foundations of our own existence. The universe's history is written in the light that reaches us now, and the James Webb Telescope is our most powerful tool for reading that story. If you've enjoyed this deep dive into the universe's earliest days, consider subscribing to FactVerse for daily explorations of space, science, and the mysteries that still lie beyond our reach. And if you have questions, theories, or thoughts about what these ancient galaxies might reveal next, share them in the comments.
The cosmos is full of surprises, and by staying curious, we keep unlocking its secrets one light year at a time.